So dear students, let's discuss about the next scheduling algorithm, that is shortest job first. Now as the name says, basically we know that with each process there is a burst time associated with that, uh, which basically specifies the length of that process in terms of the burst time. That means for what span of time that process needs CPU to do its execution. So we are taking into consideration the length of that burst to schedule the process for execution. So as the name says, the process which will be having the shortest length of CPU burst, that will be given the access of CPU first, and thereafter the next one which is in the queue having the next smallest CPU burst will be given the access of CPU, and so on. So basically SJF works on two schemes. Now as far as the first scheme is concerned, it is non-preemptive SJF. As I've already discussed with you, that non-preemptive is a scenario where once a CPU is given to process one process, that process cannot be preempted until that process completes its entire uh, CPU burst, or it needs to perform some IO activity. Then only the another process can enter the running state. So before completion of its entire CPU burst, the non-preemptive SGF cannot be removed from the running state. So that variant of the non-preemptive variant of this is also known as the same as the heading given in the slide, that is shortest job first. But there is one more variant of this SJF, that is preemptive variant, where it is named as shortest remaining time first. So as the name says, if a new process arrives with the CPU burst length less than the remaining time of current executing process, then the currently executing process will be preempted. For example, let's suppose the process P0, whose burst time requirement was of 8 millisecond, was executing, and as of now it has executed only for 3 milliseconds. That means its remaining time with CPU is 5 milliseconds. In the meantime, another process enters a ready queue which needs uh, CPU for only 2 milliseconds. That is, its CPU burst time is 2 milliseconds. So if we compare, the pending time for process P0 is 5 milliseconds, and the CPU burst time requirement of P1 is 2 milliseconds. So in that case, this process P0, whose 5 milliseconds period of time was CPU's time was left, is now preempted, and P1 will enter the running state and will execute with the CPU. So that is how the shortest remaining time algorithm works. So let's take a scenario where we'll be discussing about how it executes. So let's take the first variant of shortest job first, that is non-preemptive variant. So if you see over here, we have taken a system with 4 processes whose arrival times are given and whose burst times are also given. So one more thing over here is, though in this scenario we don't have any two processes having same arrival times. Otherwise, if two processes are having same arrival times, in that case FCFS can be used to break that tie. So suppose what I mean to say over here is, suppose there were two processes having arrival time as 2. In that case, we could have used FCFS and could have resolved that tie. So as I've already told you that before we calculate its average waiting time, first of all we need to prepare its Gantt chart. So let's do that part first of all. Let's prepare the Gantt chart for this system. So if you see over here, uh, uh, as we are taking arrival times also into consideration, so if you see, initially at time t0 there was only one process which was available in the system. So we will begin with that process only, because at time t0 only one process was in the ready queue, that was P1. So P1 is given the access of CPU, and it executes there for 7 milliseconds. So P1 basically enters the running state, executes there for 7 milliseconds. So now if you see, already 7 milliseconds have elapsed. So during these 7 milliseconds, process P2 has also entered, process P3 has also entered, process P4 has also entered. P2 came at arrival time t is equal to 2, P3 came at t is equal to 4, and P4 came at t is equal to 5. But as of now, 7 milliseconds have already elapsed. That means all three processes as of now are in the ready queue. So as the name says, we are supposed to select that process which is having minimum requirement of CPU's length. In this scenario, it is P3 which needs CPU only for 1 milliseconds. So P3 is preferred over the other two processes, and P3 gains the access of CPU first. So it executes for 1 milliseconds, that is from 7 till 8. And now this process basically completes its execution. So we are left with the remaining two processes, that is P2 and P4. Again, we'll look after which of these two processes is having a smaller CPU burst. So over here, P2 is having a smaller CPU burst. So P2 is given priority over P4, and P2 gains the access of CPU first, and P2 executes there for 4 milliseconds. That is from 8 till 12. CPU was working with process P2, and thereafter at last we are only left with one process, that is P4, which needs CPU for 5 milliseconds. So CPU executes on P4 for 5 milliseconds, that is from 12 to 17. So now the next step is to fetch the completion time for all these processes from this Gantt chart. So if we see over here, process P1 completes at 7 milliseconds, process P2 completes at 12 milliseconds, then process P3 completes at 8 milliseconds, and process P4 completes at 17 milliseconds. So now we are supposed to calculate the average turnaround time and average waiting time. So for that, first of all, we'll calculate the individual turnaround time for each of these processes, and then we'll calculate the individual waiting time for these processes. So turnaround time is completion time minus arrival time. So completion time for process P1 is 7 and arrival time is 0. So this is 7 minus 0. Fine. For P2 it is 12 minus 2, that is 10. Then we are having uh, I would say process P3, whose completion time is 8. So then arrival time was 4, so it comes out to be 4. And then we are having 17 as completion time, and the arrival time was 5. So with this 5 as arrival time, so this comes out to be 12. Fine. So now let's calculate the waiting time. So for waiting time, we will consider turnaround time for the processes. The turnaround times are 7, 10, 4 and 12 for processes P1, P2, P3 and P4 respectively. And for calculating waiting time, we need to subtract a burst time from turnaround time. So turnaround time is 7 for P1, and its burst time is again 7. So waiting time is 0. In this case, it is 10 minus 4. So waiting time is 6. In this case, it is 4 minus 1. So it is 3. So in this case, it is uh, basically our turnaround time is 12 and burst time is 5. So this comes out to be 7. So to calculate the average turnaround time, so for that we have to add the turnaround time for individual processes. We got 7, 10, 4 and 12. So adding 7, 10, 4 and 12, and we'll be dividing this by the number of processes in the system. So in this system we are having 4 processes, that is P1, P2, P3 and P4. So the outcome which we'll be getting over here, that is 7 plus 10, 17 plus 4, 21 plus 12, it is 33. So 33 by 4. So this comes out to be 8.25 milliseconds is the turnaround time for this in this system. So if we calculate the average waiting time, so the average waiting time in this scenario would be, so if you see over here, it is average waiting time, it is 0, 6, 3 and 7, 0, 6, 3 and 7. So add all these values, 0, 3, 0, 6, then 3 and 7, and we are dividing it by 4 as total 4 processes are over there. So this comes out to be 16 upon 4. So that means the average waiting time for this system is 4 milliseconds. So I hope you got the idea that how we can how actually the shortest job first non-preemptive scenario works. So let's work with the preemptive variant of SJF, that is SRTF. So as far as that variant is concerned, let's suppose the uh, system with same set of values and see how it works over here. So again, we'll start working. First of all, we'll be preparing the Gantt chart for this system. So if you observe over here, again we are having 4 processes, but now we have to do some more calculations because we are taking into consideration the shortest remaining time first. So again, at time t0 only one process was there in the system. So this process was p1. So p1 got the access of CPU, and if you see over here, at time t2, another process p2 came over there. So this process only executed for 2 milliseconds. That means out of 7, only 2 milliseconds have elapsed for process P1. So remaining time for this process is 5. Fine. But this process has not yet completed. In the meantime, after 2 milliseconds, this process came over there. Now we will compare the burst time of process P2 with the pending time of process P1. So in P1 needs 5 more milliseconds of CPU's time, whereas P2 needs 4 milliseconds of P2's time. So this P1 is preempted now, and P2 gains the access of the CPU and is doing its job. But if you see over here, 2 seconds for process P2 has elapsed. Fine. So only 2 seconds have elapsed. What happens over there? Another process P3 enters the system because it enters at time t is equal to 4. So if you see over here, only 4 seconds have elapsed over here. Fine. And by this time, P3 is there, the part of the system. So as of now, P2 was executing and it has executed only for 2 milliseconds. That means its remaining time is 2 milliseconds. It needs 2 milliseconds of CPU's time to do its remaining execution. But because P3 is the part of system now, we also need to consider the burst time of P3. So if you see over here, presently P3's burst time is minimal as compared to the other two, which were already there in the ready queue. So as P3 enters, so P3's requirement is minimal, so P3 is given the access of CPU and P3 is executing there for 1 milliseconds. So by this 1 milliseconds, that is, sorry, this should be 4 because 2 plus 2 more, so it is 4. So this basically executed till 5 milliseconds. So as of now, the execution with CPU has gone for 5 milliseconds. That is, at t is equal to 5 now, P4 has also arrived. But this P3 needed only CPU for 1 millisecond, and it has utilized the CPU. So P3 has completed its execution. So its burst time is now 0, obviously, because that actually this process has terminated now. So as of now, we are having 3 processes in the ready queue. One of them is P1, second is P2, and third is P4. Out of these 3, it is the P2 which is having minimum CPU's remaining time. So that is 2. So that means P2 is fetched now from the ready queue and is entering into the running state where it gained the access of CPU and is executing for next 2 milliseconds. It needed for only 2 milliseconds. It executed here for 2 milliseconds. So now P2 is no more the part of the system. So we are left with two processes over here. One is P1 and another one is P4, which are supposed to execute, but both of them are having same burst time. So as I've already told you, if two processes are having same CPU burst time, in that case we can resolve the tie with the help of FCFS algorithm. So we have, as we see that it was P1 which entered the system first, so we are giving P1 the opportunity to complete its execution first. So P1 again comes for its remaining period of execution. Its remaining period was 5 milliseconds. So from 7 till 12, it is P1 which executes, and now P1 has also completed. Now the remaining time of P4, actually P4 is entering the system for the first time. System means running state for the first time. So now P4 executes there for 5 milliseconds and completes its execution at 17 milliseconds. So this is the Gantt chart for SRTF scenario, that is the preemptive scenario of shortest job first. So now we will see what are the completion times of various jobs. So if you see over here, P1's completion time is, P1 actually executed twice on the system, one during this phase, then on this phase. It completed its entire execution at this time. Fine. So the completion time of P1 is 12. The completion time of P2 is, again P2 came twice for execution. So its completion time is 7. Completion time of P3 is 5. Completion time of P4 is, if you see over here, it is 17. So these are the completion times for the various processes. Now we are supposed to calculate the turnaround time, and for this we need the value of completion time as well as arrival time. So in first case, 12 minus 0 is 12. In second P2, it is 7 minus 2, that is 5. Then we are having the another scenario, that is 5 minus 4 for P3, that is 1. And then we are having 17 minus 5, that is 12. So these are the turnaround times of the processes that were the part of system. Now we have to go for waiting times calculation, which needs turnaround time and burst time. The turnaround time for P0 is 12 and its burst time was 7. So it is 12 minus 7. Fine, it comes out to be 5. For P2, turnaround time is 5. Its burst time was 4. So this comes out to be 1. Then we are having process P3 whose turnaround time is 1. Its burst time was 1. It is 0. And then we are having process P4 whose turnaround time is 12 and its burst time was 5. So this comes out to be 7. So again, using the same set of steps, we will be calculating the average turnaround time and average waiting time. The average turnaround time will be evaluated by adding these values: 12 plus 5 17 plus 1 18 plus 12 30. So total 30 is, if we add up the turnaround time of all the 4 processes and we are dividing by 4, because we are having total 4 processes, so this comes out to be 7.5 milliseconds is the average turnaround time for such a system, whereas the average waiting time for this scenario would be, again add the values, that is 5 plus 1 6 plus 0 plus 7. So 6 plus 7 comes out to be 13 divided by 4. So this comes out to be 3. 4 3s are 12. Then 1, it is 3.25 milliseconds is the average waiting time for this system. So this is how we can evaluate the uh, preemptive variant of SJF. Some more calculations are involved in this. We have to be very careful while we are basically taking into consideration that which process will get the access of CPU at what time. So if you see over here, the processes are coming and gaining the access of CPU multiple number of times because they are preempted from executing CPU in between, as their burst time was more as compared to the process which is already there in the ready queue and is having smaller burst time. So then let's see what are the various pros and cons over there with regard to SRTF. Now, as far as this SJF is concerned, basically it minimizes the average waiting time. Why it is so? Because it basically is reducing the average waiting time. That is why it is optimal. So we can, if we have evaluated this. With these set of values for FCFS also, and if you compare the two systems, we'll find that over here the average waiting time is lesser as compared to FCFS. And this system works well with batch processing kind of systems. Why so? Because if we are well aware about what are the various jobs needs well beforehand, if it is known, so obviously it will be more efficient to work with such a system, with such a scheduling algorithm in batch processing. It also maximizes the throughput, because why throughput is maximized? Because throughput basically is what the number of jobs which can be completed in per unit time. So as smaller jobs are being given the CPU access first, they are executed first, so that means more jobs can be completed in a given period of time. That is why over here the throughput is much better. Then another thing is, it is quite easy to implement if we talk of the non-preemptive scenario. We have seen this. We need to only look after which job at present is having the minimal CPU burst time and just fetch that job. So I'm saying non-preemptive version is quite simple as compared to preemptive version, where we need to take into consideration the pending time of the currently executing process, and also we need to look into the ready queue, that whether a new process has arrived which is having lower CPU burst time as compared to the currently executing process. So there are some more calculations are involved. So actually non-preemptive version is quite simple. Now, next thing is about disadvantages about of this SJF. So yes, it is quite difficult to know priorly for what span of time a process will be requiring CPU to execute. So it is quite difficult to estimate the job length. Then there is also involved a risk of starvation. So what happens over here is, because the jobs which are having smaller CPU burst, they are getting the excess of CPU as compared to the one with the which are having longer CPU burst. So in that scenario, if processes with smaller CPU burst keep on entering the ready queue, this will lead to starvation for the processes which are having larger CPU burst time. So this may lead to their indefinite postponement. That is, they have to wait for quite a long period, and there might be a chance that they will never execute if new processes coming in the system are having a smaller CPU burst time. Uh, Also, these systems are not suitable for real-time systems, uh, because these systems do not consider deadlines of priorities, but they don't take into consideration deadlines or priorities. They only look after the burst period. If the burst period is small, that job will get the excess of CPU. But even if suppose there is a process which is having a larger CPU burst period, but their job is of higher priority, this algorithm doesn't take into consideration such scenarios. Then if we talk of the preemptive version of SRTF, so if you see over here, uh, the number of context switches which were done in SRTF is more. So that is why the overhead in SRTF scenario, that is the preemptive variant of SJF, the context switching is the number of time the context switching is done is more. So that is why the overheads are on the higher side. So that is the drawback of SRTF. Then as I've already told you, basically we need to have a prior knowledge regarding the process times, and sometimes it is not feasible to know the prior to have the complete knowledge of for what span of time a process might need the CPU. So in that case, it is a difficult kind of thing. So that's all about shortest job first, preemptive as well as non-preemptive variant. So in the next slide we'll be in fact in the next video we'll be discussing about the round robin scheduling. So till then, thank you.